So far, we've derived two kinematic equations. In this video, we will derive the third equation, which combines the first two equations to allow us to determine the position of an object at some instant in time in the future if we know the acceleration of the object. Let's begin with equation 2, which defines the final position being equal to the initial position plus the average of velocity multiplied by time. You will notice that in this equation, the final position is not dependent on acceleration, but we know from previous videos that any change in velocity is caused by an acceleration. So we can use this fact to add acceleration to the equation. Recall from equation 1 that the final velocity is equal to the initial velocity plus the product of the acceleration and time. We can thus substitute final velocity in our second equation with equation 1. Expanding the inner brackets thus gives us the following equation. Finally, we can expand the remaining brackets to give us a final position being equal to the initial position plus the product of the initial velocity and time plus the product of half of the acceleration and time squared. This is our third kinematic equation. We can also write the equation in terms of the displacement. Let's revisit the helicopter problem, where a rescue helicopter drops an emergency kit to a broken down boat at some distance below. In the last video, we determined that this distance, or the displacement, was 20 meters. Let's now use equation 3 to also calculate the displacement, but this time using what we know of acceleration instead of the velocity. The facts that we have gathered from the previous exercises is that the time taken for the kit to fall was 2 seconds. Its initial velocity was 0. The acceleration was 9.8 meters per second squared downwards, and the final velocity was 20 meters per second downwards. We have defined the downward direction as positive. So equation 3 is displacement being equal to v0 t plus half at squared. We can now substitute the values for initial velocity, acceleration, and time into the equation. The answer is also 20 meters, which is consistent with the answer in the previous video. A typical performance indicator of sports cars is how long it takes for the car to cover a quarter mile, which is 402 meters. In the last video, we calculated that the Ford Mustang Boss 302 has an average acceleration of 6.2 meters per second squared while going from 0 to 100 kilometers per hour in 4.5 seconds. Assuming that the car can maintain this average acceleration over the quarter mile, what is the fastest time the car will take to cover the quarter mile? The Mustang takes 277 meters to decelerate from its maximum speed of 259 kilometers per hour to a complete stop without skidding. What is the deceleration during this time? A third equation of motion defines the final position being equal to the initial position plus the product of the initial velocity and time plus the product of half the acceleration and time squared.